Yeah, so I'll be talking about some of our work, like our efforts to enhance our scientific understanding of deep learning. So I'm kind of preaching to the choir here, but deep learning is obviously amazing. We can, we have these amazing chatbots. It's made significant strides in like scientific applications, and I can even, generate a photo of me giving this presentation right now. But it seems like, a lot of tasks have like effectively been solved by scaling up these models, so-called foundation models. So like, what is left for us to do? I'd like to go back to like over 10 years ago with like the seminal AlexNet paper. And it totally, upended the field and made everyone rethink like what the future of machine learning would be. And although there are a lot of efforts in scaling up these models and also coming up with new applications and engineering these models, there are a lot of, investigations into the science of these models, spanning theory, optimization, interpretability, and just coming up with new algorithms. So I think now in like the era of these large foundation models, which are very large and, solving very complex tasks, we have even more opportunity to like understand and exploit emergent phenomena of these large scale models. So today I'll be discussing, our efforts to try to understand and exploit some very intriguing phenomena of these models. So first I'll talk about shared representations in vision models, the diffusion model weight space geometry, and finally an unexpected and surprising mechanism in vision transformers. So to begin with the shared representation in vision models, I'd like to start with a famous bet in some academic circles. So my advisor, Alyosha Efros, made a bet with his advisor, Jitendra Malik, that if by the first day of autumn of 2015, a method will exist that can match or beat the performance of RCNN on Pascal VOC detection without the use of any extra human annotations as pre-training, Mr. Malik promises to buy Mr. Efros one gelato. So this is the famous gelato bet. And basically, in a nutshell, it's unsupervised pre-training can beat ImageNet trained models for object detection. So although Alyosha lost this bet, he was very prescient and he actually ended up, being right many years later. And the underlying intuition is basically that vision models will learn meaningful deep features regardless of their task. They don't need labels. So think about like a self-supervised proxy task such as masked autoencoding, where you have an image, you mask it, and you're basically training to reconstruct the image. And then you can actually repurpose this model to use it as a classifier. Or similarly, if you have like an ImageNet classifier, you can repurpose this model and use it as like a segmentation model. So even though these models are trained on different data sets and have different tasks, there must be some notion of like animal, pose, background, etc. So in our work, we hypothesized that there must exist some common internal representations among these different vision models. And we focus on common neurons, which refer to the individual channels of convolution filters or the individual dimensions of like multi-layer perceptron layers in ViTs, for instance. And as I proceed with the presentation, please feel free to stop me at any time and ask any questions. So prior work, such as like David Bao et al., investigated the meaning of individual neurons in vision models. So what they do is feed in a bunch of images into CNNs and basically correlate them with segmentation masks from an off-the-shelf pre-trained segmentation model. And they found like very interesting and meaningful units. So for instance, there'd be a neuron that fires for a dog or a neuron that fires for plants. But a limitation of this is that it'll only detect segment-related neurons. We're, bottlenecked by what, the segmentation model was trained on, and those were trained using human labels. And we know like the world is much richer than, words that can describe, objects. So in our work, we want to do this in an unsupervised fashion from the ground up and discover what are common neurons among various vision models. So how we go about doing this is we have a generative model, and we'll just sample a bunch of images from this model. We'll then feed this into a discriminative model, such as CLIP or Dino, and we'll cache the activations from all the neurons among these models. Next, we'll just correlate all of the activations across all these models and just take the mutual nearest neighbors. So for instance, if this neuron, its best match is this neuron in the generative model, and this generative model's neuron's best match is the same neuron in the discriminative model, we would consider that a match. So how do we go from 2 models to a zoo of models? So we'll basically start with a generative model kind of as our anchor. So in GAN, for instance, and then we'll repeat this matching across multiple discriminative models. Then we'll only keep those neurons which match with the same core set neurons in the generative model. So essentially, by some sort of transitive property, all of these neurons will align with each other. And we call these neurons the Rosetta neurons because the Rosetta neuron, the Rosetta Stone was an ancient artifact used to translate between different languages. In this case, we're translating between the language of different models. So we can actually visualize what these neurons are firing for. So for instance, we see that this one seems to be firing for the cat's red hat. And then we can see very interesting, semantics emerge. So for instance, we see like a nose detector, an eye detector, a contour detector, which is really interesting because we actually didn't explicitly use labels. And there are also some other interesting neuron firing patterns that we observe. For instance, we see like certain textures which cause neuron activations to fire, or something like more abstract, such as like contact with the ground, which is at the bottom row. So now that we've found these neurons, like what can we use them for? So we can actually use these to translate between the language of different models. So consider the task of inversion. So in classic GAN literature, what you could do is, given an input image, you would optimize your latent code such that you would best reconstruct that image. And the idea is by projecting it into this latent code, you can apply edits or do some sort of manipulations on this image. But this is an under-constraint optimization, highly non-convex. So what we can actually do to guide this is essentially use our Rosetta neurons. So we can input our image into a discriminative model. And then we have these Rosetta neurons that we know match between different models. So what we're going to do is just optimize this latent code such that its Rosetta neuron activation patterns match those of a discriminative model. So essentially, we're kind of doing this cross-model translation. And what we find is that we can actually project this image into the language or the manifold of this generative model. So here are some instances of what this can look like. So to the left, we have what some of these neurons look like. And then top row is the input image, and the bottom row is what the reconstruction is. So for instance, we can see like the first example with the cartoon horse, like the GAN language, it was trained on these Shutterstock images of horses. So it will reconstruct something with Shutterstock. And then we can use this similar optimization technique to decode what individual neurons are actually doing. So for instance, if we take a look at the first row, we see that it's firing for this red Santa hat. So we can generate a bunch of counterfactual images which are explaining like what would produce these sort of neuron activations. So if I were to decode this neuron, like would anyone venture to guess like what sort of images we would be generating? Don't be shy.
A hat? The hat?
Yeah, so that's a good answer, and like that's what I was expecting. So like it seems like it's a hat, but what we see is that it actually generates a bunch of cats which have like red in the background. So for instance, the first instance is a Santa hat. If we take a look at the second example, it's like some red like poster or something in the background. So this is actually like generating counterfactuals, and we see that this neuron is actually firing for the color red. So that's like a powerful technique. Rather than just visualizing one instance, you can actually generate counterfactuals, which would induce this sort of neuron activation pattern. And we can do like similar thing for other neurons. So for instance, we can generate other cats, which would induce this contour activation pattern. So some other things we can do with this neuron is basically.
Can I ask a question?
Yeah, go ahead.
These activation inversions, are these like similar to like dataset samples, for example, that the neuron is maximally activating for?
Yeah, that's a really good connection. So it's basically like that, except it's more expressive because we're actually optimizing. We're basically like optimizing an image that would create this.
Okay. So even if it's randomly optimized, it's still producing cat images?
Because we're using a GAN, or like a generative model, so it needs to produce like realistic images.
Okay, awesome. Thanks.
Great question. So we can go even further and like elicit some hidden capabilities from the generative model. So these, for instance, with GANs, they're very prone to mode collapse, where they like produce very canonical, non-diverse images. So they'll be very centered, object-centric, usually just one object. And if you just like indefinitely sample from these generative models, you'd never be able to get very interesting images. But what we can do is actually like intervene on these neurons. So we can zoom in just by zooming in to the neuron, or shift this neuron, or even copy and paste. And this copy and paste is, I think, particularly interesting because like these generative models, like at least GANs from a few years ago, would never really generate very complex like multi-object scenes. Or for instance, if you're generating like a cup of beer, the samples are going to be biased towards like always having some liquid in it, or a waterfall is always going to be biased towards having some water in it. So by intervening on these neurons, we can actually elicit some, or steer the model in some way which we would not get if we just kept on sampling from it. So in this work, we showed that vision models' internal representations have some converged properties. So Philly Sola and his group have come up with this really interesting work called the Platonic representation hypothesis, which argues something even stronger, that neural networks trained on like completely different modalities, such as text and image, are also converging. So if you're interested in this line of work, I highly recommend you also take a look at this work. So in summary, for this work, we found that like certain visual concepts and structures are just inherently embedded in the natural world, and they'll be learned regardless of your data, and regardless of your architecture and your task. And we found like very common internal representations without using semantic labels, and showed some applications where we can communicate between different models. So if we take a look at this iceberg from my intro slide, we've just scratched the surface. We've taken a look at activations and neurons. But if we want to dig even deeper and understand these models, we'll want to look at the weights that actually give a rise to these activation and neuron patterns. Which leads me to our next part of the talk, where we try to understand the geometry of the weight space of diffusion models. So linear latent spaces, these subspaces of some input data, has been largely studied for decades. So for instance, in the 90s, there was a lot of work on like applying PCA to face images, and they found that you can morph faces and produce new faces just by doing interpolation of subspaces within subspaces of pixels. Then later on with GANs, people found like used data sets of latent vectors and found subspaces within them. So you can actually like edit images and do these nice interpolations in some semantic subspace. So for instance, if you had a face, you could add a mustache by following some direction in the latent space. Now, in this work, we go like a level up in abstraction, and we want to understand the weights of these models. And essentially, in a nutshell, we have a bunch of fine-tuned diffusion models, and we find that we can do some interpolation within this weight space of diffusion models and generate a completely new valid model, which generates some concept. So for instance, here, it generates my advisor. So how do we get these models? So we start with a pre-trained diffusion model, which is like the current de facto standard generative model. And we just fine-tune this on a small set of training images. So essentially, we're injecting this novel concept into the diffusion model. And we repeat this over 60,000 times for different identities. So we get 60,000 different diffusion models encoding a different person. And these weights live in this very, very high dimensional weight space. And we want to model the manifold that these weights lie on. So our hypothesis is actually, rather than lying on some very complex nonlinear manifold, these fine-tuned models actually form a linear subspace within the weight space. And this is inspired by like a lot of empirical as well as theoretical work on like very linear properties of deep neural networks. So essentially, we find that this is true. These weights live in some very low dimensional linear subspace, and we call this weights to weight space. So we just define this subspace by compressing it into a set of PCA bases. And we call this like a meta-latent space, because typically with like a generative model in the latent space, you will map from some latent to an image. But in this context, we are mapping from some low dimensional latent space into a completely new model. So I'll demonstrate some applications of this space. So typically with a generative model, you'll sample some noise in your latent space, and it'll generate a new image. But in this low dimensional weights to weights weight space, we can sample model weights. And this parameterizes a completely new diffusion model, which encodes a new identity. So for instance, it's generating this man, and we can prompt this new model with, this man close-up of a face, or playing tennis, or with a celebrity. So here I show like each row is corresponding to samples generated from a sampled model. And then we take the nearest neighbor in weight space to the set of models that we use to define our weights to weight space. And interestingly, these weights actually sort of seem like a form of like a similarity metric. So they're like some sort of representation. So for instance, in the first row, we see this man has like a very strong jawline and long hair, which is similar to this nearest neighbor model. And then now we can also edit models. So in generative models, you might want to edit your image, but here we're editing the model itself. So we have a bunch of labels that are corresponding to these models. So for instance, a model encoding one person might have a beard, whereas the model encoding a different person may not have a beard. So using these labels, we can define a hyperplane just by applying a SVM on these weights. And then if we traverse orthogonal to it, we can actually edit the model. So now this person will now have a beard, for instance. And this is actually not like image editing. This is actually editing the model itself. So once you apply this edit in weight space, all of the images of this person will now have a beard. So what's really cool is that by operating in weight space, and we are parameterizing a new model. So for instance, each of these columns is a new model. The edits are super fine-grained and don't interfere with other concepts that the model is encoding. And finally, like my favorite application is that you can typically with like a generative model, you may want to invert into some latent code. But here we're actually projecting this image into the weights of the model. So what we'll do is we'll basically optimize and interpolate within this weight subspace, and it will parameterize a completely new diffusion model, which now encodes the identity in this image. So typically with like fine tuning, if you fine tune on a single image, you'll like catastrophically forget all the rich priors that you learned during your pre-training phase, and you'll just like produce that one image. But since we're constraining our optimization to live in this weights to weight subspace, which is essentially like a prior on what your model weight should be, you're able to like personalize your model to an instance without forgetting all the priors that it learned during pre-training. So for instance, here I can generate my advisor, in Paris, reading a book. And yeah, the loss is just your typical diffusion objective, but now we have a constraint that it has to live within this weights to weights subspace. And in practice, we can just do this by directly optimizing like the principal component basis coefficients. And what application I think is pretty cute is, since we define this manifold of weights to encode realistic identities, if we give it like an out of distribution identity, so for instance, the guy from Up or a sketch, it'll project it into a realistic model. So for instance, it'll produce this Up guy as like a realistic person, but then we can also prompt the model to generate paintings or in like a variety of scenarios. And then we can even go beyond like human identities. They say that pets look like their owners. So we can even give it like an animal, and then we'll project it into weights, and they'll encode this human, which is like kind of looks like this dog. And like these semantic subspaces within the weight space of diffusion models is not just restricted to faces. We can also like fine tune our diffusion models on different concepts. For instance, like different dog breeds. And then we can also find like semantic subspaces, such as like making dogs have wavier fur or being larger, or even like things which are not natural, like cars. There's like a car subspace within the weight space of diffusion models. So in summary, we showed that there are disentangled linear subspaces of these visual concepts in weight space of diffusion models. And essentially, we created this like meta latent space, like a very simple generative model over weights. So going back to our iceberg, we've looked at activations in neurons and weights, but so far, we've corresponded these units to very interpretable human things that humans would label. So for instance, like faces or like object parks, things that correspond to features. But if we really want to understand like deep learning, we also want to understand like very complex interactions between components. So this will lead to my final topic, which is an unexpected mechanism in vision transformers. So in this very seminal paper, Vision Transformers Need Registers, what they found is that as you scale up these ViTs, there'll be like very intriguing artifacts within the internal features. So if you take a look at the output patches of Dino V2, for instance, there'll be these patches which have like very high norms, and they don't seem to be like corresponding to anything meaningful. And this leaks into the attention maps. So if you take a look at the attention maps of these models, we also see like these very weird high norm artifacts. And this is very contrary to what we would think. We would think that the attention would focus on object parks and things which are like semantically meaningful. So what they propose is essentially augmenting your standard vision transformer with these learnable so-called register tokens. And the idea is that these tokens would learn to absorb these high norm outliers and then clean up your attention maps and your internal features. And this would lead to cleaner attention maps and also better prediction for dense tasks, such as depth estimation, segmentation, as well as unsupervised object discovery. And after applying this, we see that the attention maps are much cleaner. But this is not just, specific to vision transformers. People observed a similar phenomenon in large language models. So for instance, Detmer et al. Found that as you scale up these models, at a certain scale, there will be these outliers that emerge, and this really messes up like quantization. So as you can see, quantization with naive methods works pretty well until a particular scale, and then once these outliers emerge, the performance of like quantized models just drops. And furthermore, like in this paper, they found beyond just like outlier features that this leaks into attention maps. And we can see that, like, for instance, in the language model, it's putting all of this attention into the first token. And they call this an attention sink because this, during the attention operation, this first token is essentially acting like a sink, and all of the other tokens are dumping attention on this. And this has implications if you want to apply your language model in a streaming setting. So you want to, chat with your chatbot indefinitely. And like, this is really like, this is a very, like real problem. And for instance, like GPT, they just released some open source version of GPT, and you can see in line 243 that they add these like learnable sync registers. So we've motivated this problem. So a lot of work has observed that these high norm tokens emerge, but in this work, we understand like what is the mechanism that leads to these high norm tokens emerging in the first place. So we begin with open clip ViT model, and we track the maximum norm of patches across multiple components, the attention and the multi-layer perceptron layers. And what we observe is that layer 6 of this model, after the MLP, the norms just explode. And then subsequently, the attention scores suddenly rise, suggesting that now like the outlier has occurred and now attention sync has happened. So it seems that since it happened right after the MLP, maybe this is what's causing the issue. So let's look at the neurons of the MLPs. So to the left, I have an input image, and at the bottom, I have the output patch norms. And we see that there's this weird outlier occurring in the background. And what we observe is that there are a certain very small set of neuron activation maps which have a very high correlation with where these outliers are occurring. So for instance, in OpenClip, only 10 out of 40,000 neurons show this phenomenon. So this leads to our hypothesis that a small, consistent set of sparsely activating neurons control where the outliers emerge. And we call these register neurons. So to go about finding these neurons, what we'll do is we'll have our image, we'll feed it through our transformer and collect all of the activation maps of this model. And we have the output of this model, and we'll just take the norm. And we see that there are these outliers that occur. And essentially, we go through all the activation maps in the model and correlate each of the activation maps with the outliers. And we see here, for instance, that this neuron has a very good correlation with where the outliers are occurring. And we call this a register neuron. So, so far, all of our observations have been purely correlational. We saw that these neurons happen to fire where the outliers are occurring. But we need to be more scientific, and we want to see if there's a causal relationship. So here I show like an input image and then the attention map of the model at the last layer. And what we can do is we have the register neurons, and they're very outlier activations. And what we can do is we can actually shift those activations anywhere along the tokens. So we can shift it from one token to another token very early on in the computation of the transformer. And then if we do that, so for instance, we can place it into a smiley face, downstream at the output of this model, now we see that there's a smiley face that emerges at the in the last layer's attention map, showing that these neurons are actually very highly causal. And if you're interested, we have some more quantitative experiments in our paper quantifying this causality. So if we can shift them anywhere in the image, why don't we just shift them outside the image? And we shift it into a dummy token called a test time register, and now we clean up the attention maps. So how do we create these registers at test time without training anything? So we'll feed our image, do our typical patch embed in a vision transformer, and we'll initialize this dummy register to a vector of zeros. Then we'll go through, and once we encounter this register neuron, we'll basically take the max activation and shift it into this dummy token and zero out our map. And then just proceed with our computation. And interestingly, we do a linear probe of various tokens, and we find that these registers and these outliers have a very high performance in classification, almost as good as the CLS or class token, which suggests that these outliers and registers actually hold global information. So you might be wondering, like, why do we even have to move these activations into a dummy token? Why can't we just zero them out? Well, actually, these activations hold global information. So if we just zero it out, it'll destroy the performance of the model, which we'll see later. So we have to shift it somewhere so that the model can use it during its internal computation. So now we see with a test time register, we get a very nice clean attention maps, just like we would with the trained register. And this gives us a pretty nice performance boost for zero-shot segmentation. And if we do linear probing, we can maintain our ImageNet classification performance, but we get some gains on more dense prediction tasks, such as segmentation and depth estimation. And we get performance that matches that of using registers that were trained. And we get significant improvement if we want to do unsupervised object discovery. So for instance, typically people will want to use the internal features of these vision transformers for some downstream task. Maybe they'll apply PCA or use some spectral clustering or some algorithm. And we see here with using a test time register, the internal features are much cleaner for these downstream tasks. So now to debug, we can actually apply these post hoc to any model without training. So what we can do is actually just apply it to an off-the-shelf vision language model because we don't need to train. And we find that this is actually a very useful tool for debugging the VLMs without affecting its performance, without hurting its performance. So for instance, if we give this image and ask which spot is this red car parked on, the only really valid answers are 30, 31, 32, and 33. And what we see is like the model, for some reason, spits out 28. And if we take a look here, we have the patch norms of the vision encoder. And we see that there are these high norm tokens that are occurring in the vision model. And in the middle, we're actually not visualizing the vision model. We're actually visualizing the LLM itself. So here we're taking a look at the attention pattern of the model's response 28 to the vision tokens that have been injected into the language model. We see that it gives like these very uninterpretable high norm artifacts. So we don't really know what's going on here. But when we include a test time register now, we see like the patch norms, there are no outliers. We have a much more more uniform, less skewed distribution of these norms, and the tension looks much cleaner. So we basically get like a text condition attribution, and we can see now like, okay, this 32 upside down kind of looks like a 28. So we can get some nice like visualization of the language model's attention now with the register, and we can maintain the performance of the VLM. We don't actually by injecting this test time register, we don't mess around with its internal computation. So so far I've shown how do these high norm tokens emerge, and I've shown some applications with vision transformers. But it begs the question, like, why do these high norm tokens even emerge in the first place? So some works have like investigated this. So for instance, in this work, they find that attention sometimes needs like an implicit bias term. So what I mean by bias is basically some constant term that is always injected into it. And they find that like if you learn some constant key and value terms here in this augmented attention, you can actually get rid of these outliers, these high norm tokens. So it suggests that basically these high norm tokens emerge as a way to induce some implicit attention bias. And to mitigate this, as they were saying, they propose to add some learnable bias terms, K prime and V prime. Another attempt to answer this is from this work here. And what they suggest is that as you scale your transformer width and depth, basically you have a very, your representation for your task is sufficiently built up at a particular depth. And since attention has this constraint that softmax has to sum up to 1, it has to contribute something to this residual stream here. So it needs to add something to the representation. But if you already have like sufficient representation, you want to minimize your update. So they suggest that basically by having the attention do nothing, a no op, it basically mitigates these outliers, suggesting that the transformer dumps all of its attention onto one token in order to minimize its effect during the attention computation. So based on this, I will give a mathematical model that gives an intuition for how register neurons can induce these high norm tokens. So I'll talk about how a register neuron can induce the attention sink. So a high norm token that just absorbs all of the attention. And then how this will lead to like this no operation. So it gives a bit of an intuition for like how register neurons kind of cause these. So let's consider like a very simple like transformer. We have W1, W2 with some activation function. These are your MLPs. And we'll have a attention layer, which just has identity projection. And then we'll just have some output head. And just without loss of generality, we'll consider we just have 3 tokens and we're applying our head to the first token, the CLS token. So we'll feed these tokens through, and after the first MLP, we'll get some activations. And then if we take a look at what the state is at this point in the residual stream, it's the original token plus some vector. So essentially we can just replace this. It's just some vector in this residual stream modulated by some coefficient. But we can construct like a register neuron, which corresponds to a column and row of these 2 weight matrices. And if they live in the null space of this matrix here, as well as the output head here, and let's say this token will become our attention sink, and it's aligned with this register neuron here, it will induce a very large activation, and it will write this vector into the residual stream. So essentially this x2 is just being some u2 vector, which is in the null space of w head and w12 here. And because it has a very large activation, it'll have a high norm token. And then when we go to the attention layer, we'll just focus on the CLS token, since that is what's being used for the task. And basically, the CLS token is going to be mixing some information from the other tokens. So it's assigning some probability based on softmax to the other tokens. And because x2 is very high norm, it will dominate the softmax and essentially have like a probability of 1. So really, the CLS token's update will just be the CLS token plus this x2 token. And we can just substitute in what our x2 token is. Next, we'll proceed with the next MLP layer. and what it writes into the residual stream right before this output head. And we do some simplification, and because our U1 and U2 live in the null space of W1, 2, and the head, if we simplify, it gets mapped to 0 if we apply W head. And this is equivalent to there not being attention in the first place. So basically what we've shown is that with a particular parameterization of these register neurons, we can show how this register neuron will induce a high norm token, which will soak up all the attention and basically induce a null update from the attention. So it kind of unifies this idea of having a no op. So there's some empirical connections that this mathematical model happens to have. So if you remember, like a register neuron lives in this, the kernel of W12 and the head. And because it lives in the null space, the kernel, when you apply this transformation, it will map to 0, which suggests that it's uninformative for the task. And what we observe empirically is that these register neurons in the output outliers actually occur on like semantically unmeaningful regions, such as backgrounds or uniform texture. And even in language models, people have observed that these outliers occur on like commas and like basically, again, some semantically low information tokens. A second connection is that basically this null update is essential in order to maintain like the quality of our representation. So the underlying intuition was basically if the, for instance, CLS token is already sufficiently built up its representation for the task, we don't want to change it. So we want to have a null update from the attention. But if we disrupt this null update, the attention is going to unnecessarily affect the CLS token, which will degrade its performance. So what we do is we actually zero out these register neurons in order to disrupt this, no-op attention behavior. And what we observe is that this like drops the performance of OpenClip for zero-shot ImageNet classification. It drops by like 15–16%. But if we just ablate random neurons, it has like a minimal effect. So it suggests that these like register neurons are highly causal and very responsible for something during the attention operation. And then finally, register neurons seem to induce this implicit attention bias. So if we take a look, our update during attention for the CLS token was the CLS token before the attention plus some beta U1 plus alpha 3 U2, where these live in the null space of W12 and the head. And what we empirically observe is that actually the register neuron activation seemed to be constant and high across a variety of images. It doesn't really change. So basically then our beta and alpha 3 are going to be constant. And essentially we're just, during the attention operation, we're just adding a fixed vector, which is basically serving as a constant bias. So this connects to this paper I was talking about previously, where they suggest that the outlier tokens effectively have induce some sort of bias in the attention operation. So what we do to test this hypothesis, the hypothesis that register neurons induce an implicit attention bias, is we just set this K prime and V prime to the mean key and value features of the test time register. So rather than learning it, we basically have a test time register and average its key and value features across 1,000 images, and we inject this into the attention layer. And then during inference, we just don't use the test time register, and we just zero out those register neurons. And what we find is that with this attention bias, we get basically the same attention maps as using a test time register, and we mitigate these artifacts. And we also maintain like the internal computation and maintain the zero-shot ImageNet performance. So I provided like a bit of a poor man's theory of like how these register neurons are like leading to high norm tokens and maybe what their contribution could be. So overall, like the takeaways are that we find like a sparse set of neurons that explain the main mechanism behind register tokens and outliers. And we can mimic the effect of these learned registered tokens, but without retraining. And this, is a this raises a very interesting point that like previously we were looking at weights and neurons as relating to some sort of feature related role. But here we investigated a very complex mechanism that shows that neurons don't have to be feature related. They can be some input independent term. So we've really like spanned this entire iceberg, but there's a lot more to do. So in this talk, I was talking about how we can understand and exploit emergent phenomena in deep networks. And this led to some simple test time optimization or gradient-free intervention during inference. But what I think is like a very exciting direction is like, can we actually do this during training rather than thinking about it as like an afterthought? So with that, I'd like to thank my collaborators, and I'd like to open up to any questions.
There are some questions in the chat. Maybe I can just read them out. So had a question somebody asked, how do you go about which activations to pair between different GAN and discriminator?
Sorry, could you repeat that?
Yeah, so how do you go about which activations to pair between different GAN and discriminators?
So
I think it was related to the first one, yeah.
Yeah, so basically we have some generative model and we'll collect all the activations. And we have the discriminative model and we'll collect all the activations. And we'll basically, so we'll have, X activations from the GAN and we'll have Y activations from CLIP, for instance. And then we'll take the Pearson correlation between all of the neurons. So we'll end up with like an X by Y table that is where each index is a score that shows what is like the correspondence between neuron X and neuron Y between the different models. And then like the thing is though that, X by Y is very big. We need to like distill this into a core set of neurons. So what we do is basically, we just take like the neuron, if we have like a neuron X, we'll say like, okay, what is the neuron in the other model which has the highest similarity to this neuron? And let's say it's neuron Y. Then we'll also take a look at like from the perspective of neuron Y and say, okay, what is neuron Y's highest scoring neuron in the other model? And then we just, so basically only keep the mutual nearest neighbors.
Okay, awesome. There was another question, like, are you saying that there is some resemblance of universal patterns that the models are learning? I think this was also related to the first paper.
Yeah, so yeah, that's the argument that basically there are universal patterns that these models are learning. Even with like different data, different architectures, different tasks. And I think like a big part of this is like, as we scale up the data, the patterns, like, there are a certain set of patterns which are, defining our natural world. So as you scale the data, then like, where there's going to be a lot more overlap of what the patterns are between these different data sets.
Got it. And I had another question. So again, regarding the first paper itself, so we saw that hat detector neuron or like the contour detector neurons. So were these all like the ones you observed, were these all like lower layer neurons, like that were identifying, let's say, a color like red or like a contour?
So your question is,
Are
are they
these like,
lower like are like the lower like
I
the
mean,
more
yeah, are they similar to like the lower layer
yeah
neurons in the vision models?
so that we did observe that. So typically with like discriminative models, they start with like very low level features, and as you go deeper and deeper, they'll develop some abstractions. But then it's like the opposite with the generative model. The generative model starts with the abstraction, like, okay, it knows it will generate a dog, and then it starts to refine it and focus on lower level details as you go deeper and deeper into the network. So that's what we observe here. So for instance, with the generative model, like these low level texture is occurring at like very late layer 31. Whereas with something like, a ViT, we see that it's happening in like the first layer.
Right. And then the next question that I had was like, did you observe any kind of superposition kind of phenomenon in the data that you tried to observe? Like,
yeah, that's a great question. So I think that based on so like also like for anyone who's maybe not super plugged into like the interpretability literature, superposition basically means that you can have like a neuron or some basis which is not just corresponding to one feature. So for instance, you can have a neuron that fires for like dogs, but then also fires for like bananas. So I think like based on our algorithm, it biases it towards finding monosemantic features. So things which are, just corresponding to one feature. And the reason is we take this correlation, and the chance that a neuron, let's say we have a neuron that fires for two concepts. The chance that like two neurons which match on like one of the concepts also like match for like the second, superimposed concept is like very low. So we didn't observe that.
Okay, awesome. All right. So if anybody else has any questions, please feel free to unmute yourself and ask, or you can also post it in the chat. Okay, Joanna, you can go ahead.
Hi, thanks. Thank you so much, Amil. It was very insightful. I want to ask a little bit more a research direction for the diffusion model example. You said about training, not training, but creating models based on other models' weights. I wanted to ask, what's the computational cost of this? Because you're not training the models directly, you're creating weights based on other models. But would it be possible to do such an experiment with like simple CPU setup, or is it still computationally expensive?
Yeah, so you're talking about the weights to weights. So I think like first of all, like you do have to have like a set of 60,000 models or like a big set of models. So this part is computationally expensive. I mean, like we're able to do it with like it's actually pretty easy to do this with academic compute, because we're not doing like full fine-tuning of the entire model. We're doing like LoRa's, so like these low rank adapters that are added. So like this was still, you need like, I don't know, having like some 8 GPU setup is nice. So that part is expensive, but like for creating like completely new models by like interpolation. So for instance, like these applications, once we define this subspace, are super lightweight.
Yeah, that makes sense. Thanks.
Yeah.
Yeah, yes. On the same lines, like, would you be able to share some ideas with us that could be low compute but still like interesting, low hanging fruits or something that we could as a community work on?
Yeah, so I think like a lot of the basically anything that is like not training is accessible. But even like if you want to use like the new like GPT models that were released, like they're like I think it's like 120 billion. So that's still like can't fit on a single GPU. So even like saying like low compute, it can span like a pretty large.
Yeah.
So if you mean like CPU, I think it's like pretty difficult to do anything.
Yeah. Nothing is possible with CPU. Yeah.
Yeah, but I think like with like one GPU, like I think like coming up with just like there are already like existing methods, so you can just like probe like pre-trained models and find some like interesting phenomenon. But I think like also very interesting is basically coming up with toy models that that can like explain some interesting phenomenon, maybe like some theory regarding that. Because like I've been like recently I've been like very surprised by like how predictive some theories have been. So I think that that's also a very interesting direction. Even like doing stuff with like, you know, even like deep linear networks without like activation functions, you can probably have, like CPU and like NumPy, and you can get and like come up with some like very interesting you know, findings.
Okay, awesome. Yeah, that was great. So yeah, if anybody has any questions, feel free to ask, or if not, we can probably end the session here. Thank you so much, Amil, for taking out this time to chat with us today and answer all of our questions. We really appreciate it, and we really look forward to reading and implementing your papers, and might reach out again in future.
Yeah, thanks for having me.
Of course. Thank you so much. Have a great day. Bye.
Bye.